and gentlemen, welcome to the Notes on 3-4.
I preempt this broadcast because I just wanted to let you know that I'm recording a video of an old video. I know, kind of weird. I'm hearing myself from last year on November 13th, and this is November 15th, 1 year and 2 days later. So that's kind of weird. Yes, I understand that. So let's listen to myself and see how silly I was last year.
On this really gray November 13th. Lunch. Not really a lunch since I don't eat, but that's okay. We're talking about properties of logarithm functions. Probably won't get through this whole video during my lunch, so I might have to postpone some of it. All these rules that you see right here, the product rule, the quotient rule, the power rule, those are all things that we talked about in Algebra 2. You know, you'll remember this one. What am I writing for? You'll remember this one, the third one, from the movie The Lion King. I believe that's the movie. Is it the one? Let me think about this. If that's the movie. No, it's not The Lion King. What am I thinking? Holy cow. It's the... what? Okay, it's the one with the little ferret. He's the king. I can see Madagascar. That's it. It's Madagascar. Okay, gotta get my writing tool here. Madagascar.
Yes,
Okay,
Madagascar.
They sang about it in that movie. Madagascar.
His name was King Julian.
I think you remember the song that I'm referring to, right? I like to move it, move it. You like to move it, move it. We like to move it, move it. Move it! Yeah, and they're talking about the exponent to coefficient property, or back from the coefficient to the exponent. You can move it.
You know, that was a great version of that song. Don't even try to tell me it wasn't.
Because you like to. That's right, folks.
Oh, what did he say? I think I said something important. Let me go back.
You can move it because you like to. That's right, folks. That's what that song was all about from the movie Madagascar. Please tell me I spelled that right. All right, anyway. So just as a review to you on some of these properties, let's see here. We definitely see the addition going on here, so we are going to be multiplying here. The 2 and the 18 get multiplied together, so...
How do we know we should multiply? Because the property of logarithms that we just had up there called the product rule, which unfortunately I can't scroll down to. I could maybe rewind it to a touch. Will it go back, or is it gonna...
About from the movie.
Okay, so you can see that product rule up there. And what I really want you to notice is, so in this particular property, we've got two things. And maybe I should explain this to you in case this doesn't make sense to you. Whenever you are in this example that we're talking, this simplified example that we're using, we're taking something from this side and we're going this way. That's where we're writing things as single logs. And I know several of you want to start singing right now, you know? Oh, the single logs, oh, the single logs. I'll let you keep going with that one. But that's what's happening. We're using, anytime you are taking these properties and you're going from this side to this side, you're changing it into what we call a single logarithm, okay? I think this book might use the phrase condensing or simplifying or something like that. But when you are transferring things to single logarithms, now, what's the coefficient of every single logarithm in the universe? I think you'll notice it's a 1. That's the coefficient, so keep that in mind. For single logs, we have a coefficient of 1. So maybe I should squeeze that in here. Coefficient equals 1. Now, that's not true when we go on the expanded side, which, you know, we'll have to look at later. Expanding means we're going this way, right? That's expanding. Not just what you do on Thanksgiving after you eat a lot of food, okay? Not naming any names, it would be myself anyway. Anyway, so expanding moves to the other side. Now, what you'll notice when you move to the other side, and this is maybe hard to see in this, and I'll try to highlight it. Maybe I should use like a yellow. I'll try to use yellow. I don't know if this will show up very well. Nope, did not show up real well. Okay, we'll use a dark green. Every single argument of every single logarithm has an exponent of 1. So the arguments have exponent equal to 1. Okay, that's what you get on the expanded side. Anyway, thought I'd share that with you, and I'll clear this off and we'll keep going with our video of myself. This is, this is the first time I've ever done this. It's kind of weird, and I think cool all at the same time.
Madagascar, please tell me I spelled that. Some of these properties, let's see here. We definitely see the addition going on here, so we are going to be multiplying here. The 2 and the 18 get multiplied together, so this is equivalent of a log base 6. 2 times 18 is 36.
Amen.
Now, you and I both know that's equal to something, so we can set it equal to a variable, and we can continue to simplify this. Folks, if you tried to do this at home without a calculator, you wouldn't know what to do.
That's very true. Because remember, a logarithm is an exponent, and the exponent on 6, which gets me 2, it's less than 1, but it's some weird decimal. Let's go ahead and listen to Brother Staley as he continues to preach.
For instance, nobody knows what the exponent is. It's some kind of weird fraction for the exponent on 6, which gives you 2. And who the heck knows what the exponent is on 6 that gives me 18? But because of this really cool product property,
Preach it, brother.
we can combine this because we see addition there, and we end up with this, which can be changed into its other form. 6 to the x equals 36.
Now remember, when we did this in class, I used boxes. I've noticed over the years that you guys struggle with it. And so I use a box and another box and then another box on the other side of the equal sign. The arrow that you just saw me draw in there is another way to think of it, starting with the base down here, then you go to your exponent, and it equals that thing right there. But same concept or strategy, just change it to exponential form. So let me clear that off. This is truly a great idea.
We know that 36 can be rewritten as 6 squared. What am I writing? 6 squared. It's wrong. So that must mean that x is 2. Remember how we talked about if the left side equals the right side and the bases are the same, then the exponents have to be equal as well. So we're using the property to put those two things together. What if, and I don't think this is farther down the road, yeah, what if we had something like log base 6 of 72 minus log base 6 of 2. I mean, who the heck knows what these things are? They're weird decimals.
Nobody.
But because we see subtraction, we know that we can take the 72 and the 2 and we can divide the arguments.
That's right.
1 log, wow, it's a really big log there. 1 log, let's see if we can, make that look normal, somewhat. And that's log base 6 of 36, which we know that equals some number in the universe, and whammo, wow, this looks so familiar. So even if I can't tell you what those weird decimals are, right? Because both of these things up here are going to be weird decimals, okay? How do I know what their difference? Well, I can use this property. I can tell you that the difference between those two logarithms, and we know that one word synonym for logarithm is
Exponent.
exponent. That's
Oh,
right, it's an
yeah.
exponent, okay?
I don't know if you know this, folks, but this is exactly what's going to happen to me someday in the nursing home when I don't remember, because dementia runs in my family. So they'll be sitting these videos down in front of me, and I will just think they're hysterical, and it's really just me. Anyway, so this is kind of a flash forward in my life.
Yes, you do have a weird math teacher. Remember this stuff. Okay.
Amen.
We know your last math teacher wasn't weird enough because you didn't remember it from then. Unless you had me, and then of course you might remember it because I am the weird one.
Yes.
Okay. Let's see. Assuming x and y are positive, use properties of logarithms to write this as a sum of logarithms or multiples of logarithms. Okay. I see 8 times x times y to the fourth. Okay, it's time to split that up. We're going to have 3 separate things separated by addition, right? Why do I know it's addition? Because this is a product. Okay, so the cool thing is we have a base of 10, right? That's a common log, so we have log 8, log x, and log Now, that is not what we call expanded form. Remember, our goal here is to expand. One of the things you need to remember is that expanded form has exponents equal to 1.
Yep, for the argument.
Exponents equal to 1. Clearly, this is in violation of the
not a 1.
expansion property.
Amen.
Because it's not a 1. So what are we going to do with it?
Move it.
Because we like to move it, move it.
Amen.
All right, so that's what we're going to do. Obviously, this one has an exponent of 1, and this one has an exponent of 1, but this one did not.
It does.
However,
now.
We used our properties to put it into expanded form. Obviously, if you're trying to write things as a single log, you'll be going the opposite direction, and all of these things will be moving in reverse order. So first, obviously, you would move that coefficient right here, make it an exponent. And then, of course, you would see addition and combine everything together to get back to the beginning. But that would be something where you're going the other way, where they would say write as a single logarithm.
Oh, the single logs.
All right. So here's a quotient. See, these are more difficult than what you had last year. Okay? I don't really like the way they've written that. But you can tell that they're using base E. We do have, this is really the same thing as the square root of x squared plus 5 all over x. They should have written it more like this.
Amen.
That way you can tell.
Yep.
But, they didn't. So, first thing I see is a quotient. I can split that up. So we have the natural log of the square root of x squared plus 5. Okay, make sure that's all underneath there. Minus the natural log of x. Then I got to do more work here, so that would be the natural log of x squared plus 5 to the 1/2 power. Got to
remember that? Square root is the 1/2 power. I think some of us are forgetting that, and we need to make sure that you remember how to write roots as fractional exponents and what they mean.
Remember that stuff, folks. You can't just get rid of it just because you didn't want to remember it was for the square root was the 1/2 power. And then, of course, what are we going to do with this? We're going to move it. That's right, 1/2 times the natural log of x squared plus 5 minus the natural log of x. Now,
one thing I do want to say to you, and I might be redundant, and I might say this to myself in a few seconds, is right here, I see kids that think they should be doing something with that. That is not a product. You cannot split that up. Don't try to split that up. Don't try to create your own logarithm properties which aren't even true. And that's what we find a lot, is that people misuse the properties a bunch. Let's see if I say that to you again in the video.
Don't get crazy on me and think you can start distributing that 1/2.
Yeah, that's
Okay.
bad too.
These parentheses right here protect the x squared plus 5.
Amen.
There is no property in the universe that says you can separate that x squared. You can't have natural log x squared plus natural log of 5.
That right there, yes. I'm glad I made that point. You cannot split that up. It doesn't work that way. The property says you can split up a product, not a sum.
It would be completely in violation of several international laws, and in some countries of the world you might lose a limb for that. So don't use the properties the wrong way.
Amen.
I'm just warning you. I'm just trying to help you. I want you to hurt yourself. Condensing. Okay, that's the idea of writing it as a single logarithm. So now we're going backwards. Things like, making this an exponent. So we'd have natural log of x to the 5th minus natural log of xy quantity squared. And then because you see subtraction here, we can then divide these. What am I dividing? Folks, we are going to be dividing this over this. X to the 5th over xy quantity squared. Now, can we do anything with that? Oh, yeah. So that's the natural log of this. There's a little bit of reducing that can happen there, right? Because you got the natural log of x to the 5th over x squared y squared. And yes, a little...
Okay, now just to remind us, this exponent will move that around, and I shouldn't be. This exponent is getting distributed to both of those. So if you were wondering where I was coming up with x squared and y squared, it's that distributive property. It's called the power of a power. We learned about it back in Algebra 1 and in Algebra 2. Let me clear that off and make way for what else I'm going to say. This is fun. I like doing this.
Basic reducing is in order. So for instance, you can get rid of that, change it to a 3, get rid of that. So natural log x cubed.
Now, just so if you're wondering, yes, I did use the idea of subtracting 5 minus 2, because when you divide like bases, okay, once again, can't move that around. Subtracting like bases, the 5 minus 2, that's where we get x cubed. If that still doesn't make sense to you, remember, you have x times x times, there's 5 of them on top and there's 2 of them on the bottom. So you can sit there and say, okay, well, how many of them cancel out? That leaves 3 of them in the top. If you're wondering if that doesn't make sense, or if I went too fast, which it kind of makes me think I did. But anyway, I digress. Let me continue.
Over y squared. Single logarithm.
Remember, single log has a coefficient of 1. And clearly out in front of that logarithm is a coefficient of 1.
Oh, by the way, the coefficient of a single log.
Yeah. We already know.
Out there.
We talked about it earlier.
Single logs.
Oh my goodness. Who wants to listen to this guy? I do. Who am I kidding?
If you like it, then you better put a bass on it. If you like it, then you better put a bass on it. You know what I'm talking about.
Yeah.
All right,
I know. We've heard it before.
The coefficient for a single logarithm is none other than 1. Okay? Now, we're never going to write the 1. We don't want to be uncool at the parties and get thrown out.
Amen.
So we won't write that. But the thing that you've got to remember is if that coefficient is not a 1, then you're going to have to use the move it exponent property.
Amen.
Right, where you take that coefficient and you move it up and make it an exponent. But we didn't have to do that this time.
Nope. Not this time.
Okay. I shall return to work on this video later when I have more time. So, bye for now.
Okay. How come there's so much space? What? Where'd all that come from and then disappear? All right, maybe it'll come back here in a second. Okay, pause the video for station identification. This is the All Pre-Calc Network. All right, to continue, sports fans, we're working on these logs. These particular logs you're looking at right here, you know, normally we would set them equal to x, and then we do like the 3 to the x equals 16, but none of us know how to write 16 as a power of 3. That's right.
Because it's some whacked out weird decimal.
Whacked
That's
out.
why we have this change of base theorem, which says that you can change any...
Wait a second. Change of base theorem from algebra 2? Okay, let's see what I have to say.
Any logarithm you want into any other base, as long as, it would be a pretty crucial thing that you not choose 1, but any base you want. Now, we typically choose base E and base 10 for obviously reasons, because our calculators can handle those. Now,
hold on, I need to go back. I feel like I didn't do a very good job of explaining. So let's see here. So what we're getting at is, with this particular theorem, is if you'll notice, this is, let me get my tools. Okay, my writing tools, that is. This is the argument, and this is what we would call the old base. Okay, now, if we analyze this, this is saying log, and we get to pick whatever base we want. So even though I'm writing an A right now, I hope you realize that that's a choice that I'm making. And a lot of times we do base E or base 10 because our calculators can handle that. Okay? But if you'll notice where they moved the X and the B, that means that we take the log of the argument over the log of the old base. And when we do this, we can solve a question like example 5a, because we can just do log 16 over log 3, which is, I'm sure, what I'm about to do. But I just wanted to slow that down because it seems like I was skirting right through that theorem right there, and I needed to slow my roll a little bit. Okay, let me clear that off and resume. Where are my controls? Oh, there they are. Okay.
But any base you want. Now, we typically choose base E and base 10 for obviously reasons, because our calculators can handle those. Now, I do realize that some of you people have your cheater calculators that will allow you to change the base without, so, you know,
that
could be a great no calculator answer.
Oh, I like
that.
that.
No calculator. Well, right here, this is a no calculator answer.
Nice answer.
Because it's been changed to base 10. So, we could have some situation like that. So this is going to be
awesome.
Log 10 over log 6. Of course, everybody in the room should know that log 10, I mean, I know you're not in the same room with me. I'm just saying.
Yeah, I know.
Everybody should know that log 10 is equal to 1.
Why is that? Why is log 10 equal to 1? Because remember, it's the exponent. Remember, logarithm equals exponent. It's the exponent on the base of 10, which gets me 10 to the first. So that's why it's equal to 1.
Because that's the exponent on 10, which gets me 10 to the first. Of course, then you'd have to, you know.
Seems like there's an echo, like we're out in the mountains or something, and there's like an echo in the distance. I say it, and then I say it again. It's weird.
Type the rest of that on your calculator to get some weird decimal. Or, you know, log 2 over log 1/2, you know, things like that.
So I know that those are things you can type on a calculator. And yes, you will get weird decimals. Those are not questions that will have, like I said earlier, if you're going to do no calc, the only way to do no calc on that is to leave your answer as an expression. You know, look at every single time I've done this, I've been leaving the answer as an expression. I didn't find you the decimals. I could reach over, grab the calculator and do that, just like you. But if this were a no-calc portion of a test, then I literally would be asking you to leave your answers in those forms. I digress. To get that weird decimal, wait a second. 1/2 to the x equals 2. I should be able to do that without a calculator.
Oh, I should.
Because that would be 2 to the negative first to the
Oh,
x
yeah.
equals 2 to the first. That would be, I could multiply those together, so that would be negative x has to be equal to 1. So that means x equals negative 1. Okay. Now see how we rewrote it into its exponential form, and then we took the 1/2 and changed it to 2 to the negative first. Then we compared the exponents. So we have negative x equals positive 1, so obviously x equals negative 1. Okay, so I didn't need a calculator on that one. All right. So, but could have used one. Graphing logarithmic functions. Okay, we know that all the log functions look very similar. Okay. Describe how to transform the graph of the natural log function into the graphs of the given functions. Sketch the graph by hand and support your answer with a grapher. Okay, so we got log 5, and so what they want to do here is they want to use the change of base, right? And if I use the change of base, I can choose log of the argument over log of the old base, you know. All right, now, we did that, but just slow it down and think about it. Now, some of you are saying, well, why are you transforming the notation from log to ln? Just remember, I chose base e because they told me to. Up here, they actually instructed me to do everything based on the natural log. Well, so they're forcing me to use base e. And so that's what I did. So I'm rewriting, you know, this thing right here into its base e form. And then we're going to look at it and see how that plays out in terms of shrinking and stretching and reflecting, because that's going to do some stuff. You know, all of you should know that log base 5 of x looks something like that, right? In fact, if I switch over to Desmos, I could show that to you. Log base 5 of x, and ln x is not going to be that much different. It's just a different base, but it's going to look similar to that. And so let's see what else I have to say. Don't move around. I don't know what's going on. There. That's a broken record from what we learned. And maybe I should have said that back here. Clear it. It's, you know, that right there is the argument. Oh, right? Now that's I'm saying it. That's the old argument right there. Man, yeah, I should have slowed it down. And that's the old base. Yeah. Right? The old base. Glad I said that earlier. So if I say that in the future, log of the argument over log of the old base, you'll know what I'm talking about. I'm referring to that change of base theorem. Okay, so all they did to this thing was they altered it by changing the base, and that's what you can see right here that they did. Well, the natural log of 5, right, is we can say that if that's equal to y, then we can do a little fireproof form changeover here by moving this thing to the other side. So that would be the natural log of x equals, let me zoom in here, the natural log of x is y divided by 1 over the natural log of 5. Okay, what the heck is he doing now? I think there's a better way to handle that. Because that, I know right now that most of you are going to say, how does he do that? Okay. I want you to keep in mind that, we could say that we're multiplying both sides by the natural log of 5. That's one way to say it. It almost would be better if we took our calculators and found the decimal version of this. So if I took my calculator and typed ln5, I get some weird decimal. Looks like 1.609. So what if I'd said what if let me write this down. What if I changed this to the natural log of x over 1.609? Okay, I'm just gonna round to the thousandths just to make my life easier. So if you want that to go to the other side, some of you are going to say, well, Mr. Staley, why don't you just say the natural log of x equals 1.609 times y? Well, that's true. But remember, fireproof form has y by itself in the numerator. And so we could go through that process that we did in class where we would multiply by the reciprocal to the top and the bottom. And basically what that's going to do is, so it's going to move that thing to the denominator. Well, if you take 1 divided by that 1.609, you end up with 0.622. All right, I think that's, and if I'm just going to do the 1 over natural log 5 just to make sure. It's actually 0.621. Okay, so, if we do the more accurate version, this thing right here is 0.621. So instead of writing it like this, I could write natural log x equals y over 0.621. Now that's really fireproof form. So you should all be screaming at me, oh, Mr. Staley, that's a vertical shrink, because that number is less than 1. And you guys are all about to walk in here for a test, so I better pause this video for now and come back to it after school. Pause. Okay, I'm not sure where we were because I stepped out of the room for a second. Bye. Oh, I forgot.
1 over the natural log of 5.
Okay.
1 over the natural log of 5 is 0.62. So we're talking about a shrink, right? Vertical shrink. Now, if you get to this one right here and you do the same trick, all right, natural log of x over natural log of 1/4.
Okay.
All right, so look at the algebra they're doing there. So
oh my goodness.
This is using one of the properties that we haven't even talked about yet.
Wait a second. We have talked about that property. He's lying to you, folks. That property was up there. That's the quotient property. We've already seen that. So I don't know what he's talking about. Okay. How did he get his math degree?
Well, actually, no, we did. We just did that in the previous video.
Yeah, that's what I'm talking about.
So,
try to lie to
natural log
us.
of 1 minus natural log of 4. Well, we know that the natural log of 1 is a big fat 0.
Amen.
That's why it disappears.
That's right. That's right.
So we can rewrite this. Look, it's a multiplier times the natural log of x. Now, we can then, in the fireproof form, switch that to the other side, right?
Hopefully you
so
show
we
it
would
to
have
us.
y divided by that weird fraction.
Oh my
negative
goodness,
1
this isn't very
the natural log of 4.
Yeah.
Equals the natural log of x.
Why don't you just change it to a number?
They show you here that the 1 over the natural log of 4 is this 0.72, so we know that it's a vertical shrink, but we also know that there's a reflection across the x-axis because of that negative.
Okay, I need to explain that because he's doing a bad job. All right, so if we would rewrite this as y, well, gotta stop that. Y equals negative 0.72 times the natural log of x. It would be so much easier if he would have just written it like this, and then we could have just done this where we divide by negative 0.72 to both sides. I used yellow because you could see it better on the black screen. Okay, and then that's going to be gone. And now I can easily see that it's got the two parts that he just described. Okay, the shrink, the vertical shrink going on there of the 0.72, and the reflection across the x-axis. Both of those things we have done a bazillion times in class. Okay, those two things right there. So it's once you get it changed into its other form, it's much easier just to find the number and then deal with it instead of all this fancy schmancy algebra stuff. Anyway, that's just my take on it. We'll see what else he says here. Let's clear this out and go back to what he say. So they're using the change of base theorem to see what kind of stretch or shrink is happening here. Now, yes, you need to know your basic log function. Well, they should already know that stuff. And all of them look pretty much the same. They all have 1, 0. They all have the same domain and range. Now, when I say they all have the same domain and range, be careful. As long as they all look like this form. Right, no shifting. As soon as we start changing that logarithmic form and throwing things together that are unusual or different. And what he means by that is shifting left or right. That's when you start changing domain and range, or domain. Your range is going to be all real numbers, negative infinity to infinity, so I don't think you're going to affect that much. It's just your domain that could be affected if you go left or right. If you're shifting it up and down, you ain't changing nothing on the domain. That's going to make some things look weird. But no symmetry to the graph, you know it's increasing, left to right, it's always increasing. Whoops, I missed my 1, 0. Oh my goodness. Shame on me. Exactly. There's no local extrema, no mins or maxes. Of course not. No horizontal asymptotes, definitely a vertical asymptote at x equals 0. Amen to that. There's end behavior, and like I showed you on your quiz, I asked you, how about this? I said, what's going on as you go, approach 0 from the right? Of course, that's negative infinity. Yeah. As you can definitely see that dropping down. As you're coming in from this direction, closer and closer to 0, it's going down, 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 down. Amen. Okay. So, on the next question, so here's some data. You might want to pause the video and get this data entered in your calculator. Okay. If you want to play along. So let's do that. A little station identification, pause for the All-Trig network. So if you've got the data entered in list 1 and list 2 of the calculator, this is list 1, this is list 2. Yeah, okay. Let's see what they're going to ask me to do. I'm guessing some type of regression, but this question says re-express the AT data pairs in table 3.2 as the natural log of A and the natural log of T. In other words, we could, so let's do that. So at the top of list 1, go all the way to the top, and you have to be highlighted on L1. Hit natural log L1. And do the same thing to list 2. Go all the way to the top and type natural log list 2. In other words, we're going to be affecting both the x's and the y's. Now, it says rewrite the linear expression in a linear regression. So, okay, so let's see here. I'm going to have to switch over to my camera. Bear with me while I get my camera set up here. We are bearing. All right, so I got my data here. Got it. And cool. If I do natural log L1 and natural log L2. Okay, so I should have the same data you do. Okay. Pause it and make sure it's the same data. Okay, if we don't have a data entry problem, that's going to mess up a whole lot of stuff. Okay. We're going to do a linear regression. So stat, calc, linreg. Now we're calling it list 1 and list 2. and we're going to calculate this thing. All right? I'm going to snip this for a second. Snip it. So you can see what I'm going to write here. Okay, do it. Oh, you should have done it bigger than that. Okay, now. Okay. All right, you didn't. There's my linear function, but what I want you to realize is that it is not y equals, it's the natural log of y. Okay, that's an important point right there. If you've transformed the x's and the y's, in whatever way you've done that, in this case, natural log x and natural log y, then don't look at this right here. Whoa, stop moving. Don't look at this right here and say, oh, it's just y and x. It's not. It's the natural log of y, and then pretty soon I'm going to write down something involving the natural log of x. But we're going to get to the test, and I'm going to ask you a question somewhat like this, and I can't tell you how many kids just write y equals. It's not y equals. It's the natural log of y equals. So hopefully you'll pay attention to that. No, gotta press this, then I press this. And over here, yeah, we got 1.499 times x, but it's not x, it's the natural log of x. And I'm running off screen here for no good apparent reason. Exactly. Plus 6.952. Okay, good enough. Okay, now so I hope you understand it, because it's not x and y anymore, it's natural log x and natural log y. Exactly. Now there's a reason we're doing that, because this function, which you may not understand, is based on another function. Let's use our powers and our thoughts here on what we could do with this and see if we... Are those superpowers? That's what I really want to know. We can, let's say we want to solve this for y. So let's see what we can do here. We can definitely move this up and make it an exponent. So we'd have natural log y equals the natural log of x to the 1.499 power plus 6.952. Okay. Now what? Try to think how we can, hold on a second. All right, as you probably noticed my mistake earlier, right here it says times 10 to the negative fourth. So that's times 10 to the negative fourth. So this number right here is a really small number. In fact, I'm going to erase something that I've done here and see if I can... Erasing? The book talks about, which I don't necessarily totally agree with, but I understand what they're getting at. Hold on. This is such a small number, it's almost insignificant. Right. We should call it 0. And if you look at this, you have 1.5 times the natural log of x. So what they're going to do in order to get the x's and y's together, or to look at what you have, is to put x and y on the same side, giving you the natural log of y over the natural log of x. And to be truthful, you can use the change of base property. Okay, I would never do it that way. Okay, now think about it like this. I think we should go back to that idea of what we just talked about. Take that 1.5, move it up here, and make it an exponent. So then we would have the natural log of y equals the natural log of x to the 1.5. Now we've talked about this in class. If the left side equals the right side, and the bases of the logarithms are the same, then what do you know about these arguments? What do you know about these two things? They have to be equal. So that's what we're really dealing with, is this particular function. It's a power function. We just found a power function for this particular group of information. And the other method, yeah, you can do it that way. I don't necessarily think I think that's a bad way to do it. That particular algebraic move, in my opinion, is not helpful. So we'll see if I say anything more useful here, but I think that's a much better way to handle that question. Reverse, and that would give me the log base x of y. Boy, that's a terrible way. Y would be the argument, x would be the old base, and it equals 1.5. 1.5 could
I should just skip
exponent
this.
Equals y, and evidently this is Kepler's third law.
Okay.
This is not exactly this, so I will see you in class. Okay, yeah, I definitely think we should skip all that jazz with dividing by natural log x and change it into base. Okay, do it the way I did it. Okay, see you in class.